There are moments in science that shake the very foundation of what we thought we knew. And right now, we are standing in the middle of one of those moments. For nearly a century, the Big Bang Theory has stood as the most widely accepted explanation for the origin of our universe. It painted a picture of time itself having a beginning, of matter and energy bursting forth from a singularity, and of the cosmos expanding and evolving into the galaxies, stars, and planets we see today. But then came the James Webb Space Telescope, our most powerful tool yet for looking back across billions of years, and what it found may very well be rewriting cosmic history. The shocking discovery? Webb has detected quasars, hyperbright, active galactic centers powered by supermassive black holes that exist far earlier in the universe than the Big Bang model ever predicted. These discoveries suggest that enormous black holes, the kind that should take billions of years to form and mature, were already alive and blazing less than 1 billion years after the supposed beginning of time itself. This is not just a small discrepancy. It's not simply a case of the numbers being off by a little bit. The presence of quasars at such an early stage calls into question our entire timeline of cosmic evolution. How could objects that require such immense growth and structure exist almost immediately after the universe's birth? For decades, astronomers have worked under the assumption that the Big Bang gave rise to the first atoms, then stars, then galaxies, and only after an unimaginably long stretch of time could such massive black holes appear. Yet here we are, with JWST revealing evidence that contradicts this carefully constructed sequence. What makes this even more shocking is the confidence scientists had in their prior models. The Big Bang Theory wasn't just a guess. It was supported by multiple lines of evidence. The cosmic microwave background radiation, the abundance of light elements, and the large-scale structure of the universe. All of it seemed to fit neatly together like pieces of a puzzle. But JWST's discoveries are like finding puzzle pieces that don't belong to the picture we thought we were building. They force us to ask whether we're missing a whole new layer of cosmic truth. Are we wrong about how quickly black holes can grow? Are we wrong about how galaxies form? Or are we wrong about the Big Bang itself? This is where the intrigue begins. The James Webb Space Telescope wasn't just designed to take pretty pictures of distant galaxies. It was built to probe the very limits of space and time, to see back so far that we could glimpse the first light in the cosmos. In doing so, it has become more than just a telescope. It is a kind of cosmic detective, peeling back the layers of history, uncovering secrets that the universe has hidden for over 13 billion years. But as with any great detective story, the deeper we look, the stranger the clues become. These early quasars are not just anomalies. They represent cracks in the walls of a theory that has stood for generations. The Big Bang model may still be correct in many ways, but these findings suggest that either it is incomplete or that some fundamental assumption in our understanding is flawed. And in science, when the foundations are shaken, revolutions follow. Think of how Newton's view of the universe gave way to Einstein's relativity, or how relativity is now being challenged by quantum mechanics. Each time, humanity had to let go of a comfortable certainty and step into a larger, stranger, and more fascinating reality. JWST may be nudging us toward the next leap. The idea that quasars, these powerful, brilliant beacons powered by unimaginable black holes, could exist so soon after the Big Bang forces us to rethink what we thought was settled. It makes us wonder if our universe had a different kind of beginning, or if perhaps the Big Bang is only part of the story. Could it be that the universe is older than we think? Could it be that black holes are born in ways we never imagined? Or could it be that our most cherished theory of cosmic origins is not the final word, but merely one chapter in a much larger cosmic tale? What makes this moment so electrifying is that we don't yet know the answers. All we know is that JWST has opened a door into a universe more mysterious than we ever dared to dream. It is not an exaggeration to say that we may be living through a turning point in human knowledge. a time when the very nature of reality is being called into question. And it all began with a telescope looking back into the depths of time and seeing quasars where none should exist. Quasars are among the most extreme and captivating phenomena in the universe, representing a cosmic powerhouse unlike anything found in our own galaxy. At the core of every quasar lies a supermassive black hole, a gravitational behemoth with a mass millions to billions of times that of the Sun. These black holes sit at the centers of young galaxies, surrounded by swirling disks of gas, dust, and stellar material. As this material spirals inward toward the black hole, it doesn't simply vanish quietly into oblivion. Instead, it accelerates to incredible speeds and heats up due to friction and immense gravitational forces, producing staggering amounts of energy. This process creates an extremely luminous region around the black hole known as an accretion disk, and it is this disk, glowing across multiple wavelengths, including visible, ultraviolet, and X-ray, that makes quasars shine brighter than the billions of stars in their host galaxies combined. Quasars are not just incredibly bright, they are hyperbright, emitting energy across the electromagnetic spectrum in a way that can be detected billions of light years away. This luminosity makes them stand out as cosmic lighthouses, piercing through the vast stretches of space and time. The term quasar itself, short for quasi-stellar radio source, originated when early astronomers first observed these star-like points of light in radio surveys, only to later discover that they were far more complex and energetic than any ordinary star. Unlike ordinary stars, which burn through nuclear fusion over millions or billions of years, quasars derive their phenomenal energy output from the gravitational infall of matter into a supermassive black hole. This mechanism is so efficient that a relatively small amount of matter can produce luminosities that dwarf entire galaxies, making quasars some of the brightest objects in the observable universe. What makes quasars even more fascinating is their connection to galaxy evolution. Most, if not all, massive galaxies are thought to harbor supermassive black holes at their centers. But during the quasar phase, these black holes are actively feeding and growing, surrounded by abundant gas left over from galaxy formation. This phase is critical because it shapes the host galaxy itself. The energy and radiation emitted by the quasar can blow away surrounding gas, regulating star formation and influencing the ultimate structure of the galaxy. In other words, quasars are not just cosmic spectacles, they are key players in the story of how galaxies grow and evolve. The existence of quasars also provides astronomers with invaluable tools for probing the universe. Because they are so luminous, they can be observed at enormous distances, effectively allowing scientists to peer back in time. Light from a quasar billions of light years away began its journey when the universe was a fraction of its current age, making quasars natural beacons to study the conditions of the early cosmos. Their spectra carry information about the intergalactic medium they pass through, revealing the presence of gas, chemical elements, and even clues about the rate of cosmic expansion. In essence, quasars act as cosmic probes, illuminating the distant and otherwise invisible corners of the universe. The James Webb Space Telescope's detection of early quasars takes on profound significance when we consider just how complex these objects are. Each quasar requires a supermassive black hole and a sufficient reservoir of infalling material, which in turn implies the existence of mature galactic structures. Finding them less than 1 billion years after the Big Bang challenges everything we thought we knew about the early universe. These aren't mere points of light. They are evidence that the universe was capable of forming immense structures astonishingly quickly. The implications ripple across astrophysics, forcing scientists to rethink timelines, growth rates, and even the fundamental processes that govern cosmic evolution. Quasars are not only dazzling cosmic phenomena, but they also serve as critical tools for understanding the universe on its grandest scales. Their extraordinary brightness allows them to act as cosmic lighthouses, illuminating the intergalactic medium and revealing details about the universe that would otherwise remain hidden. Because quasars emit such intense light, they can be observed across immense distances, providing astronomers with a unique window into the early universe. The light we detect from distant quasars began its journey billions of years ago, meaning that when we observe them, we are effectively looking back in time. In this way, quasars serve as historical records, carrying information about the universe's conditions when it was still in its infancy. The importance of quasars extends beyond simply their brightness. As their light travels through space, it passes through clouds of gas and dust between galaxies. This interaction leaves signatures in the quasar's spectrum, such as absorption lines, which encode a wealth of information about the chemical composition, temperature, density, and movement of matter in the early cosmos. By analyzing these signatures, scientists can reconstruct the conditions that prevailed in the first few billion years after the Big Bang. They can trace the distribution of elements like hydrogen, helium, and heavier metals, providing vital clues about the processes of star formation, supernovae, and the enrichment of the intergalactic medium. In essence, quasars act as flashlights, illuminating the otherwise invisible scaffolding of the early universe. Quasars also play a pivotal role in mapping the large-scale structure of the cosmos. Since they are visible over enormous distances, astronomers can use them to chart the distribution of matter across vast regions of space. Patterns in their distribution reveal the cosmic web of galaxies and dark matter that underpins the universe. Studying these patterns allows scientists to test cosmological models, understand how galaxies cluster, and gain insight into the influence of dark energy on cosmic expansion. Without quasars, much of this early structural information would remain out of reach, hidden behind the veil of time and distance. Additionally, quasars are vital for calibrating cosmological measurements. Their extreme luminosity and predictable properties make them useful as standard candles for estimating distances on intergalactic scales, complementing other methods like observations of supernova. This capability allows astronomers to refine measurements of the universe's expansion rate, the Hubble constant, and other key parameters that define cosmology. In this sense, quasars are not just objects of curiosity, they are fundamental benchmarks for understanding the size, age, and evolution of the universe itself. The recent discoveries by the James Webb Space Telescope amplify the importance of quasars even further. By detecting quasars that existed less than 1 billion years after the Big Bang, Webb is providing unprecedented insight into the earliest stages of cosmic history. Each early quasar offers a wealth of information about how matter coalesced into massive structures so quickly, challenging existing models and expanding our understanding of galaxy and black hole formation. They serve as both probes and puzzles, guiding astronomers toward answers while simultaneously raising new questions about the fundamental mechanisms that shaped the cosmos. In short, quasars are more than just extraordinarily luminous points in the night sky. They are cosmic lighthouses, illuminating the infancy of the universe, revealing its composition, structure, and evolution, and acting as essential tools for probing the deepest mysteries of space and time. The study of quasars has transformed our understanding of the universe, and the JWST's ability to detect them at unprecedented distances promises to rewrite our cosmic timeline in ways that were once thought impossible. Before the advent of the James Webb Space Telescope, the scientific consensus regarding the formation of quasars was both straightforward and seemingly well supported by decades of observations and theoretical modeling. The prevailing belief held that quasars, as hyperluminous objects powered by supermassive black holes, could not exist immediately after the Big Bang. In fact, the consensus was that such objects would only appear billions of years into the universe's evolution, after galaxies had time to form and supermassive black holes could gradually grow from smaller stellar mass seeds. This belief was grounded in a combination of observational evidence, physical theory, and cosmological models that had long shaped our understanding of the early universe. At the core of this belief was the idea that black holes, especially those of supermassive scale, require enormous amounts of time to accumulate mass. Stars collapse into black holes at the end of their life cycles, forming stellar mass black holes, typically a few times to a few tens of solar masses. Over cosmic time, these black holes can merge with others and accrete surrounding gas to grow larger. But such growth is inherently a slow process. The universe, as it was understood before JWST, was not believed to be old enough in its first few 100 million years to allow black holes to reach the extreme masses needed to power the brightest quasars. The formation of galaxies was another limiting factor in this old scientific belief. Galaxies themselves are complex systems that require significant time to coalesce. In the aftermath of the Big Bang, the universe was initially a hot, dense soup of particles and radiation. As it expanded and cooled, tiny fluctuations in density allowed matter to clump under the influence of gravity, gradually forming the first stars, star clusters, and proto-galaxies. These early structures then merged and grew over hundreds of millions of years, eventually forming the larger galaxies capable of hosting central supermassive black holes. Given this timeline, the appearance of fully formed quasars within the first billion years seemed highly improbable. Observations with earlier telescopes reinforced this view. Instruments like the Hubble Space Telescope, the Chandra X-ray Observatory, and ground-based facilities had identified quasars at great distances, corresponding to times when the universe was roughly 1 to 2 billion years old. However, none of these instruments had detected quasars at even earlier epochs. Based on these observations, astronomers built models suggesting a gradual, stepwise growth of black holes and galaxies. The understanding was that while quasars are incredibly luminous and active, they represent a later stage in cosmic evolution, an emergent phenomenon that could only arise after the universe had matured sufficiently. Additionally, theoretical models of black hole growth imposed practical limits on what was considered physically possible. Accretion of matter onto a black hole is governed by Eddington limits, which define the maximum rate at which a black hole can steadily accrete matter without blowing away the inflowing gas through radiation pressure. Even under optimal conditions, reaching billions of solar masses through standard accretion within less than a billion years seemed implausible. Consequently, the notion that quasars could exist in the universe's first few 100 million years was generally dismissed as inconsistent with known physics. Cosmology, too, played a crucial role in reinforcing this belief. The Big Bang model provided a chronological framework for the evolution of the universe. By calculating the time elapsed since the Big Bang and modeling the rates of structure formation, cosmologists could estimate when various cosmic milestones should occur. According to these models, the emergence of quasars was expected to be a relatively late event in the timeline. Early quasars simply did not fit into the established narrative, and any reports of potential candidates were treated with skepticism or assumed to be observational errors or misinterpretations. Another aspect of this belief was the understanding of chemical enrichment in the early universe. Quasars require significant amounts of gas in their host galaxies, and this gas must contain elements heavier than hydrogen and helium to support star formation and the complex dynamics that feed black holes. In the first few 100 million years, the universe was thought to be dominated by pristine hydrogen and helium, with heavier elements produced only gradually through stellar nucleosynthesis. This further reinforced the expectation that quasars, which rely on mature galactic environments, would be absent in the earliest epochs. The combination of observational limits, physical constraints on black hole growth, and the predicted timeline of galaxy formation created a robust framework. Quasars were regarded as late bloomers in the cosmic story, appearing after the universe had aged enough for supermassive black holes to form and galaxies to assemble. Astronomers operated within this framework with considerable confidence, and it guided research priorities, telescope design, and the interpretation of data for decades. Yet, even within this consensus, there were hints of tension. Occasionally, surveys would reveal distant objects with unusually high luminosity or other quasar-like characteristics. These anomalies were often viewed cautiously, with scientists exploring alternative explanations such as gravitational lensing, measurement errors, or peculiar local conditions that might mimic quasar activity. None of these potential exceptions, however, fundamentally challenged the prevailing belief. Quasars existed, but they existed later, comfortably within the timeline predicted by the Big Bang model. In essence, before JWST, the scientific belief about quasars was a well-structured narrative that combined the known physics of black hole growth, the chronology of cosmic structure formation, and decades of observational data. It posited that quasars could not appear until the universe had matured, roughly 1 billion or more years after the Big Bang. Any deviation from this expectation was either dismissed or explained away within existing models. The stage was set for a paradigm shift, but no one anticipated just how dramatically this shift would occur. Then came the James Webb Space Telescope, with its unprecedented infrared sensitivity, capable of peering further back in time than any telescope before it. JWST revealed quasars shining brightly in the first few 100 million years of the universe, a discovery that did more than challenge assumptions. It shattered them, forcing the scientific community to confront a reality that did not align with decades of established thought. The problem with black hole growth is one of the most fundamental challenges raised by JWST's discovery of early quasars. To understand why these early quasars are so perplexing, it is essential to grasp the mechanics of how black holes accumulate mass and why this process is inherently slow. Black holes, by their very nature, are regions of space where gravity is so intense that not even light can escape. Their growth is dependent on the material they can draw in, gas, dust, and sometimes stars. But this accretion process is constrained by both physical limits and environmental conditions. The largest black holes in the universe, those that power the brightest quasars, have masses of billions of times that of our Sun. Building such colossal structures requires vast amounts of matter and, crucially, time. Before JWST's groundbreaking observations, the prevailing models suggested that the first black holes formed as remnants of massive stars. These stellar mass black holes, typically tens of times the mass of the Sun, would then gradually grow by accreting surrounding gas and merging with other black holes. Even under ideal conditions, this process is painstakingly slow. The Eddington limit, a fundamental principle in astrophysics, defines the maximum rate at which a black hole can steadily pull in matter without blowing away the infalling gas due to radiation pressure. In other words, there is a natural cap on how fast a black hole can grow. Reaching billions of solar masses through conventional accretion would take hundreds of millions to billions of years, a timeline consistent with the appearance of quasars billions of years after the Big Bang, but seemingly incompatible with the JWST's discovery of quasars existing less than 1 billion years after the universe began. The environmental conditions required for rapid black hole growth add another layer of complexity. Early black holes need a plentiful supply of cold, dense gas to sustain high accretion rates. However, in the first few 100 million years after the Big Bang, the universe was still in a state of dramatic evolution. The first stars had only recently formed, and galaxies were beginning to assemble from primordial gas clouds. Star formation and supernovae would heat and disperse much of this gas, making it difficult for black holes to gather enough material to grow at extreme rates. In this context, the early presence of massive quasars appears almost miraculous. The observed black holes must have grown at unprecedented rates, far beyond what conventional physics predicts. Moreover, the formation of supermassive black holes in such a short period raises questions about the efficiency of merging processes. while mergers between black holes can contribute to rapid mass accumulation. The frequency and conditions required for multiple mergers to produce billion solar mass black holes so early in cosmic history seem improbable. Galaxies themselves were smaller and less structured in the universe's infancy, limiting the opportunities for mergers and reducing the likelihood of creating supermassive black holes through hierarchical growth. This means that traditional growth mechanisms alone cannot easily explain the existence of the quasars observed by JWST. The rapid appearance of these supermassive black holes also poses problems for models of galaxy evolution. Black holes and their host galaxies are thought to co-evolve. The growth of a black hole is linked to the development of the surrounding galaxy, with feedback processes regulating star formation and gas inflow. If a black hole achieves supermassive size too quickly, it could drastically alter the development of its host galaxy, creating a mismatch with theoretical models that predict slower, more gradual growth. Essentially, the timeline of black hole and galaxy formation becomes compressed in ways that standard cosmological models struggle to accommodate. This challenge extends to the broader cosmological context. The existence of billion solar mass black holes so early in cosmic history is not merely a problem for astrophysics. It calls into question some of the assumptions underlying the standard Big Bang timeline. If such massive objects can form in a fraction of the time previously thought necessary, then either our understanding of black hole physics is incomplete, or the universe is older or more complex than current models suggest. The discovery forces scientists to confront a stark reality. The early universe was capable of producing structures and processes that were previously considered impossible. Adding to the mystery is the diversity of these early quasars. JWST observations reveal that not only do they exist, but they also vary widely in luminosity, mass, and environment. Some of these quasars appear to be in relatively isolated regions, while others are part of early galactic clusters. This variety suggests that multiple pathways might exist for black holes to achieve rapid growth, further complicating the picture. It implies that early supermassive black holes are not simply rare anomalies. They could represent a fundamental aspect of cosmic evolution that has been overlooked. In short, the problem with growth lies in the sheer scale of the discrepancy between what physics predicts and what JWST observes. Conventional models of black hole formation and accretion suggest that it should take billions of years for black holes to reach the sizes needed to power the observed quasars. Yet, JWST has now shown us quasars shining brightly less than 1 billion years after the Big Bang. This means that black holes must have grown at extreme rates, under conditions that we do not yet fully understand, or that our understanding of the early universe's timeline needs to be reconsidered. The implications of this problem ripple across all areas of cosmology and astrophysics. It forces scientists to re-examine assumptions about the earliest stages of the universe, the efficiency of black hole growth, and the formation of galaxies. It opens the door to new theories, ranging from exotic physics and direct collapse black holes to the possibility that the universe is older than we thought. Each scenario challenges established knowledge and invites a deeper, more nuanced exploration of how the cosmos evolved into the structured, complex universe we observe today. Enter the James Webb Space Telescope, the most ambitious and technologically advanced space observatory ever launched, designed specifically to peer deeper into the universe and further back in time than any of its predecessors. Unlike the Hubble Space Telescope, which primarily observes in the visible and ultraviolet parts of the spectrum, JWST operates primarily in the infrared. This distinction is critical because as the universe expands, light from distant objects is stretched or redshifted into longer wavelengths. Light that may have originally been emitted in the ultraviolet or visible spectrum by early galaxies and quasars billions of years ago now reaches us in the infrared. Without the capability to detect these longer wavelengths, these primordial objects would remain invisible, hidden beyond the reach of previous telescopes. JWST's infrared vision is complemented by its massive 6.5-meter diameter primary mirror, composed of 18 gold-coated segments that work together to collect unprecedented amounts of light. This combination of sensitivity and resolution allows astronomers to detect faint, distant objects that would otherwise be lost in the cosmic background. For the first time, we can observe galaxies forming in the universe's first few 100 million years, as well as the quasars that reside at their cores. In essence, JWST is not just a telescope, it is a time machine, capturing photons that have traveled across billions of light years and revealing events that occurred when the universe was still in its infancy. Another groundbreaking aspect of JWST is its ability to perform spectroscopy at these extreme distances. Spectroscopy involves splitting light into its component wavelengths to study the chemical composition, motion, and other physical properties of celestial objects. For early quasars, spectroscopy can reveal the presence of supermassive black holes, the characteristics of the surrounding gas, and even the rate at which matter is being accreted. This level of detail was impossible with previous instruments, which could identify distant galaxies or quasars, but could not provide a comprehensive understanding of their structure or evolution. JWST's instruments, such as NIRSpec, Near-Infrared Spectrograph, and MIRI, Mid-Infrared Instrument, enable scientists to analyze these distant quasars with an unprecedented combination of precision and depth. JWST's ability to look further back in time also stems from its placement in space at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth. This location provides a stable, thermally favorable environment, free from the distortions of Earth's atmosphere and thermal interference from the planet itself. JWST's instruments are cryogenically cooled to just a few degrees above absolute zero, ensuring that the faint infrared signals from the early universe can be detected without interference. This combination of positioning, cooling, and highly sensitive detectors allows JWST to achieve something that was previously thought nearly impossible: to capture the faint light from quasars that formed in the universe's first billion years. What truly sets JWST apart is its ability to combine these observations into a coherent picture of cosmic history. By observing galaxies and quasars across multiple wavelengths, astronomers can construct detailed models of their growth, composition, and evolution. They can determine the masses of early black holes, measure the intensity of their accretion, and analyze the surrounding environment of young galaxies. This wealth of data provides not only snapshots of the past, but also dynamic insight into how the universe transformed from a hot, dense plasma into the complex web of galaxies we see today. JWST's capabilities have revolutionized our understanding of the early universe in ways that Hubble, despite its tremendous achievements, could not. While Hubble gave us breathtaking images of galaxies billions of light years away and helped identify high redshift candidates, it could not peer far enough into the infrared to definitively observe the first quasars. JWST overcomes this limitation, allowing astronomers to detect objects that are both fainter and farther than ever before. Its instruments provide the resolution and sensitivity required to distinguish between quasars and their host galaxies, unraveling the complex interplay of matter, energy, and gravity in the universe's formative years. The telescope's first data releases have already stunned the scientific community, revealing quasars that challenge the most fundamental assumptions about cosmic timelines. These observations show that massive black holes, previously thought to require billions of years to grow, were already active and luminous less than a billion years after the Big Bang. JWST is giving scientists not only direct evidence of these early quasars, but also the tools to investigate how they formed, how rapidly they grew, and how they influenced the surrounding cosmos. In essence, JWST is rewriting the story of the early universe, illuminating corners of cosmic history that were previously shrouded in darkness. Beyond its technical prowess, JWST represents a triumph of human ingenuity and collaboration, developed over decades by NASA, ESA, and CSA. It embodies the culmination of years of engineering, scientific vision, and meticulous planning. Every aspect of the telescope, from its segmented gold-coated mirror to its ultra-sensitive instruments, was designed to maximize our ability to look back in time, to capture light that began its journey when the universe was a fraction of its current age. Its deployment, requiring precise unfolding of mirrors and instruments millions of kilometers from Earth, was a feat of unprecedented complexity. And now, it is delivering on the promise of providing humanity with a direct view of the universe as it existed shortly after its birth. In short, the James Webb Space Telescope is the ultimate tool for exploring the early universe. Its advanced infrared vision, unprecedented sensitivity, and sophisticated instruments allow astronomers to detect quasars and galaxies that formed far earlier than previously thought possible. By revealing these ancient objects, JWST is not only challenging our understanding of black hole growth and galaxy formation, but also pushing the boundaries of cosmology itself. Every photon captured by Webb from these distant quasars carries with it a story of cosmic evolution, a message from a time when the universe was still young, and a challenge to our most deeply held assumptions about how everything we see today came to be. The discovery made by the James Webb Space Telescope has sent shockwaves through the astrophysics community. Quasars, these hyperluminous beacons powered by supermassive black holes, have been observed existing less than 1 billion years after the Big Bang. To put this into perspective, the universe itself is approximately 13.8 billion years old. According to decades of cosmological models, quasars of such scale should not exist until the universe was several billion years old, after sufficient time had elapsed for galaxies to coalesce and black holes to gradually grow to enormous masses. Yet JWST's observations defy this timeline, revealing a universe far more dynamic and complex in its earliest stages than scientists ever imagined. The telescope's infrared instruments detected the light emitted by these distant quasars, light that began its journey when the universe was only a fraction of its current age. Because of cosmic expansion, this light has been stretched to longer, infrared wavelengths, allowing JWST to observe it in exquisite detail. The data show that these early quasars are not merely small or faint objects. They are fully formed, extremely luminous, and powered by supermassive black holes with masses reaching billions of times that of our Sun. This implies that these black holes must have undergone incredibly rapid growth, consuming enormous amounts of matter at rates previously thought impossible. What makes these discoveries even more compelling is that JWST has found multiple quasars in this early epoch. This is not a case of a single anomalous object. Rather, it indicates that the formation of supermassive black holes and quasars was occurring on a broader scale across the early universe. Each of these quasars provides a wealth of information. By analyzing their spectra, astronomers can determine not only the black hole masses and accretion rates, but also the chemical composition and temperature of the surrounding gas. This information, in turn, helps reconstruct the conditions in which galaxies and black holes formed during the universe's formative years. The sheer brightness of these early quasars was also unexpected. Some of the observed quasars emit more energy than entire galaxies filled with billions of stars. This intense luminosity suggests that the central black holes were accreting matter at near maximum rates, challenging existing theories about how quickly matter can fall into a black hole. According to conventional physics, there are limits to the rate of accretion imposed by radiation pressure, meaning that matter falling into a black hole pushes back with the energy it emits. The JWST observations suggest that either these limits can be exceeded under certain conditions, or that other, previously unknown mechanisms are accelerating black hole growth in the early universe. The spatial distribution of these early quasars also raises intriguing questions. Some appear in regions that seem surprisingly isolated, while others are associated with dense galactic environments. This variety implies that multiple pathways could have contributed to the rapid formation of supermassive black holes. Were some of these black holes formed through direct collapse of massive gas clouds, bypassing the slower stellar seed growth entirely? Did interactions with dark matter or other exotic physical processes play a role? JWST's discovery forces astronomers to consider possibilities that were previously relegated to the realm of speculation. Moreover, the discovery has immediate implications for our understanding of galaxy evolution. Quasars are not isolated phenomena. They interact dynamically with their host galaxies. The radiation and energetic winds they produce can heat and expel gas, regulating star formation and influencing the overall growth of the galaxy. Observing quasars so early in cosmic history suggests that these feedback processes were already shaping galaxies almost immediately after their formation. This implies that the interplay between black holes and galaxies, which was thought to require billions of years to develop, was already active within the first billion years of the universe's existence. Another remarkable aspect of JWST's findings is the precision with which these quasars can now be studied. Previous telescopes could detect distant quasars, but their capabilities were limited by sensitivity, resolution, and wavelength coverage. JWST's infrared instruments not only detect these faint, red-shifted objects, but also allow scientists to perform detailed spectroscopic analysis, measuring their velocity, mass, and chemical composition. This level of detail provides a far richer understanding of early cosmic history than was previously possible, offering a window into the processes that governed the formation and growth of the universe's first massive structures. The discovery of these early quasars also has a ripple effect across the field of cosmology. By identifying objects that challenge established timelines, JWST is prompting a re-evaluation of fundamental assumptions about how quickly matter can collapse under gravity, how black holes accumulate mass, and how galaxies assemble. Each quasar observed less than 1 billion years after the Big Bang is a puzzle piece that doesn't quite fit into the conventional picture. Collectively, they suggest that either our models of black hole growth need dramatic revision, or that there may be deeper, more profound questions about the timing and mechanics of the universe itself. In essence, JWST's discovery has transformed what was once theoretical speculation into empirical evidence. These quasars are not hypothetical anomalies. They are real, observed objects that exist in the universe's infancy. Their existence compels scientists to confront uncomfortable questions about the speed at which structure can form in the cosmos, and whether our understanding of early cosmic evolution is incomplete or even fundamentally flawed. The discovery stands as one of the most significant challenges to standard cosmology in decades, signaling that the universe's early history may have been far more active, complex, and accelerated than previously imagined. The shockwaves sent through the astrophysics community by JWST's discovery of early quasars stem from a fundamental tension. These supermassive black holes exist far earlier than conventional models of cosmic evolution would allow. According to decades of theory, black holes of billions of solar masses require substantial time to grow, accumulating matter gradually through accretion and mergers. The fact that JWST has now observed quasars thriving less than 1 billion years after the Big Bang suggests that black holes were growing at rates previously deemed impossible, or that there is a serious flaw in our understanding of the universe's timeline itself. This realization is both exhilarating and unsettling, because it forces scientists to question one of the most foundational assumptions of modern cosmology. The primary source of shock lies in the physics of black hole growth. Conventional models impose strict limits on how rapidly a black hole can accrete matter. The Eddington limit, a well-established principle, dictates that the radiation pressure generated by infalling material will eventually push away additional matter if the accretion rate becomes too high. Under these constraints, even a black hole formed immediately after the first generation of stars would require hundreds of millions of years to reach the immense masses necessary to power the brightest quasars. JWST's observations, however, show that black holes reached billions of solar masses in less than 1 billion years, a scenario that appears to violate these physical limits, suggesting that either black holes can grow faster under certain conditions or that an entirely new mechanism is at play. Another reason the discovery is shocking is the sheer scale of the quasars observed. These are not small, faint objects at the edge of detectability. They are extraordinarily luminous, radiating more energy than entire galaxies filled with billions of stars. To produce this level of luminosity, the central black holes must be feeding at near maximum rates, consuming enormous amounts of gas and dust. The fact that such massive, energetic objects exist at a time when the universe was still forming its first galaxies is unexpected. It implies that the processes that led to black hole and galaxy formation were far more efficient and rapid than standard cosmological models predict. This shock extends beyond black hole physics into the realm of cosmic chronology. The Big Bang model provides a timeline for the universe's evolution, predicting when galaxies, stars, and massive structures should emerge. Observing fully formed quasars so early implies that either black holes grew extraordinarily quickly, galaxies assembled faster than expected, or the universe itself might be older than we currently estimate. Each of these possibilities has profound implications. If black holes grew faster than physics allows, it suggests unknown processes or exotic physics. If galaxies formed faster, it implies gaps in our understanding of matter aggregation in the early universe. And if the universe is older, it would call into question fundamental measurements of cosmic expansion and the timing of the Big Bang itself. The existence of multiple early quasars amplifies the shock. JWST has not merely found a single anomaly, but has revealed a population of supermassive black holes already active in the universe's first billion years. This is not a statistical outlier. It indicates that rapid black hole formation was a common phenomenon in the early universe. Such prevalence challenges the notion that these objects are rare exceptions and implies that current models of structure formation, galaxy evolution, and black hole growth may be fundamentally incomplete. Moreover, the implications ripple through other areas of astrophysics. The intense radiation emitted by early quasars would have influenced the surrounding intergalactic medium, affecting the formation of nearby galaxies and the distribution of gas in the early universe. This means that early quasars were not just passive markers of cosmic evolution, they actively shaped the environments around them. The speed at which they grew and became luminous enough to exert such influence was entirely unexpected, creating a domino effect that challenges many assumptions about the coevolution of black holes and galaxies. Perhaps most unnerving to scientists is the suggestion that our cosmic clock may be off. If quasars with billion solar mass black holes exist so soon after the Big Bang, the timeline of the universe's evolution may need reconsideration. Are we underestimating the universe's age, or is there some unknown mechanism allowing black holes to reach enormous masses at unprecedented rates? Either answer would force a major revision of the standard cosmological model, which has otherwise been remarkably successful in describing the large-scale evolution of the universe, the cosmic microwave background, and the distribution of matter and energy. The discovery is shocking because it challenges deeply held assumptions that have guided astrophysics for decades. For years, the consensus was clear. Supermassive black holes take time, and early quasars should be extremely rare or non-existent. JWST's data overturns that assumption entirely, revealing a universe that is far more dynamic, complex, and surprising than previously imagined. The shock is not merely theoretical, it is empirical. The photons captured by JWST from these ancient quasars are a direct message from the early universe, a message that contradicts long-standing models and invites scientists to rethink the physics, timelines, and fundamental processes governing cosmic evolution. In short, what makes this discovery so shocking is the magnitude of the challenge it poses to our understanding of the universe. Black holes grew faster than expected, galaxies assembled more quickly than predicted, and the earliest epochs of cosmic history are now revealed to be far more active and complex than any prior model anticipated. JWST's observations do not just push the boundaries of knowledge, they shatter them, raising questions about the fundamental timeline of the universe and forcing scientists to consider new physics, new mechanisms, or even new cosmologies to explain the early emergence of these cosmic giants. The revelation that supermassive black holes existed so early in cosmic history is staggering because it implies that these objects reached billions of solar masses in what is effectively a cosmic blink of an eye. To put this into perspective, the universe itself was less than 1 billion years old when JWST detected these quasars, a mere fraction of its current age of 13.8 billion years. According to traditional models, forming a black hole of this size requires hundreds of millions of years of steady growth through accretion and mergers. The fact that multiple quasars already housed black holes of such enormous mass in this early epoch suggests a level of cosmic efficiency and acceleration that standard astrophysics cannot easily explain. Supermassive black holes are thought to grow in two primary ways: through the accumulation of matter via accretion and through mergers with other black holes. Accretion is a delicate process regulated by physical limits such as the Eddington rate, which dictates how fast a black hole can draw in matter without the outward radiation pressure halting the inflow. Even under ideal conditions, these limits would typically require hundreds of millions of years to transform a stellar mass black hole into a billion solar mass behemoth. Mergers, while capable of boosting mass more quickly, are limited by the availability of black holes to collide with and the relative motions of galaxies in the early universe. The JWST observations indicate that neither traditional accretion nor mergers alone can account for the masses of these early black holes. They grew astonishingly fast, defying expectations. The notion that these black holes reached their colossal size in a cosmic blink challenges our understanding of time and scale in the universe's formative years. In cosmological terms, 1 billion years might seem long, but in the context of black hole physics and galaxy evolution, it is almost instantaneous. These early quasars are essentially mature objects in a universe still undergoing its first major structural transformations. Galaxies themselves were only beginning to form, stars were still emerging from primordial gas clouds, and cosmic structures were highly irregular. Yet at the centers of these young galaxies, supermassive black holes were already fully developed, consuming matter at incredible rates and radiating energy that outshone entire stellar populations. The implications of such rapid growth extend beyond black holes to the galaxies that host them. The mass of a supermassive black hole is closely linked to the properties of its host galaxy, a relationship known as the M-sigma relation, which ties the black hole mass to the velocity dispersion of stars in the galaxy's central bulge. If black holes grew this quickly in the early universe, it suggests that galaxies must have formed and evolved in tandem at rates much faster than conventional models predict. This challenges the co-evolution paradigm, forcing astrophysicists to reconsider the interplay between black holes and their galactic environments during the universe's infancy. Furthermore, the presence of such massive black holes so early has profound implications for our understanding of the formation of cosmic structures. Black holes exert significant gravitational influence on their surroundings, shaping the distribution of gas, affecting star formation, and potentially influencing the development of galactic clusters. If supermassive black holes appeared in less than 1 billion years, their gravitational and radiative impact would have dramatically shaped the evolution of their host galaxies and the surrounding intergalactic medium. This suggests that the universe's earliest structures may have evolved under conditions far more intense and rapid than previously thought. The rapid emergence of these supermassive black holes also raises fundamental questions about the initial seeds from which they grew. Traditional models assume that black holes start from the remnants of massive stars, roughly tens of solar masses, and grow gradually over time. To reach billions of solar masses in under a billion years, the initial seeds would either have to be unusually massive or the growth rates extraordinarily high. This has led scientists to explore alternative mechanisms, including the direct collapse of massive gas clouds, which could form black holes of 10^4 to 10^5 solar masses almost instantaneously, providing a head start for rapid growth. Even with such mechanisms, the efficiency required to produce the observed supermassive black holes remains astonishing. JWST's discovery also highlights the prevalence of these early supermassive black holes. The fact that multiple quasars have been observed at these early times indicates that rapid black hole growth was not a rare anomaly, but potentially a common feature of the early universe. This realization has a cascading effect on cosmology. It suggests that the processes governing black hole formation, galaxy evolution, and cosmic structure development were far more dynamic and efficient than previously understood. It also emphasizes the need for new theoretical frameworks to account for these accelerated processes. The very existence of these early massive quasars challenges our understanding of the Big Bang timeline. If black holes could achieve billions of solar masses in such a short cosmic interval, either our models of black hole physics are incomplete, or the chronology of the early universe may need re-evaluation. It calls into question assumptions about how quickly matter coalesced, how energy and radiation interacted with forming structures, and whether the universe's age and expansion history are fully understood. In effect, these early supermassive black holes are not just anomalies. They are beacons signaling that the cosmos is more complex, more dynamic, and more mysterious than conventional wisdom allows. The discovery of these supermassive black holes so early in the universe presents one of the most profound challenges to modern cosmology. The standard model of cosmology, often called the lambda cold dark matter model, has been remarkably successful at explaining the large-scale structure of the universe, the cosmic microwave background, and the distribution of galaxies. However, the observation of billion solar mass black holes less than a billion years after the Big Bang exposes a significant tension in the model. According to lambda cold dark matter model, there simply shouldn't have been enough time or the necessary conditions for black holes of this magnitude to form so quickly. The growth rate of black holes in the early universe is constrained by fundamental physical limits, most notably the Eddington limit, which dictates the maximum rate at which matter can accrete onto a black hole before the outward pressure of emitted radiation halts further inflow. According to this principle, a stellar mass black hole formed shortly after the first stars should take hundreds of millions of years to reach even a fraction of a billion solar masses. Yet, JWST has observed black holes reaching billions of solar masses in under a billion years, implying that either the Eddington limit was somehow exceeded or unknown mechanisms allowed for extraordinarily rapid growth. This discrepancy poses a direct challenge to the predictive power of the standard cosmological model. Furthermore, the presence of these early supermassive black holes strains our understanding of galaxy formation. In the lambda cold dark matter model, galaxies form through hierarchical clustering, gradually assembling from smaller structures over billions of years. Black holes, in this framework, are expected to grow alongside their host galaxies, influenced by mergers and the availability of gas. The observation of fully formed, massive black holes in the first billion years suggests that the co-evolution of black holes and galaxies may have occurred far more rapidly and efficiently than previously thought. It also implies that galaxies in the early universe must have been capable of funneling enormous amounts of matter into their central regions almost immediately after their formation. This rapid assembly challenges our assumptions about how early galaxies accumulated mass and how efficiently gas could collapse into black holes without being disrupted by star formation and supernova feedback. The chemical composition of the surrounding gas also complicates the picture. Early galaxies were thought to be dominated by primordial hydrogen and helium, with heavier elements forming only after several generations of stars. However, the intense luminosity of these early quasars suggests that their environments were already rich enough to support efficient accretion and rapid black hole growth. Reconciling this with the expected timeline of chemical enrichment in the universe adds another layer of difficulty for the standard cosmological model. How could such massive black holes exist in environments that theoretically should not have provided sufficient raw material for their growth? Another critical challenge comes from the distribution and frequency of these early quasars. JWST has revealed multiple instances of supermassive black holes at high redshifts, indicating that their rapid formation was not an isolated anomaly, but possibly a widespread phenomenon. The standard model does not predict such prevalence, especially given the relative scarcity of massive, dense galactic environments in the universe's first few 100 million years. This suggests that either our understanding of the density fluctuations that led to early structure formation is incomplete, or that additional mechanisms, perhaps involving dark matter, exotic physics, or previously unconsidered gravitational processes, may have accelerated black hole formation. The challenges extend to the cosmological timeline itself. If supermassive black holes formed so quickly, it raises the possibility that our measurements of the universe's expansion and age might need refinement. Observations of the cosmic microwave background and redshift distance relationships have provided a consistent picture of the universe's age and growth rate. Yet, if massive structures existed earlier than expected, it might indicate that the universe's early expansion and matter distribution are not fully understood. While this does not immediately overturn the Big Bang model, it introduces tensions that demand careful re-evaluation of the assumptions embedded in cosmological simulations and calculations. Theoretical astrophysicists are now grappling with these challenges by exploring alternative models and mechanisms. Ideas range from the direct collapse of massive gas clouds into black holes, bypassing slower stellar seed growth, to the potential influence of dark matter clumps accelerating the accretion process. Some even entertain the possibility that new physics, not currently accounted for in lambda cold dark matter model, could play a role in the rapid formation of early supermassive black holes. Each of these approaches attempts to reconcile the JWST observations with the broader framework of cosmology, but none are without their difficulties or uncertainties. Perhaps the most unsettling aspect of these challenges is the way they undermine the apparent predictability of the early universe. The standard model has successfully explained cosmic expansion, the cosmic microwave background, and the distribution of galaxies on large scales. Yet, on smaller scales, particularly in the formation of extreme objects like supermassive black holes, its predictions appear incomplete. The JWST observations suggest that the early universe may have been far more dynamic, chaotic, and efficient at creating massive structures than previously believed. This forces scientists to consider not just modifications to existing models, but potentially deeper revisions to our understanding of cosmic evolution. In short, the rapid appearance of supermassive black holes observed by JWST represents a profound challenge to cosmology. It exposes gaps in our understanding of black hole physics, galaxy formation, and the early universe's timeline. The standard lambda cold dark matter model, while extraordinarily successful on many fronts, struggles to account for objects of such mass and luminosity in the first billion years. This challenge is not merely technical, it is conceptual, questioning the completeness of our cosmological framework and pushing the boundaries of what we know about the universe's earliest epochs. The unexpected presence of supermassive black holes less than 1 billion years after the Big Bang has prompted scientists to explore a range of possible explanations, each with profound implications for our understanding of the universe. These early quasars challenge conventional models, forcing cosmologists and astrophysicists to rethink fundamental assumptions about the processes that govern black hole growth, galaxy formation, and the evolution of cosmic structures. While no single explanation has been universally accepted, several leading hypotheses have emerged, each offering a potential pathway to reconcile JWST's observations with known physics, or hinting at the need for new physics altogether. One of the most widely discussed possibilities is the direct collapse black hole hypothesis. In this scenario, instead of forming from the remnants of massive stars and gradually growing through accretion and mergers, certain regions of the early universe may have allowed enormous gas clouds to collapse directly into black holes. These clouds, containing tens of thousands to hundreds of thousands of solar masses, could bypass the conventional star formation process entirely, producing black holes that are already significantly massive from their inception. A direct collapse black hole would have a tremendous head start, allowing it to reach billions of solar masses in far less time than a stellar seed black hole could. While this mechanism requires very specific conditions, such as low metallicity, minimal turbulence, and suppression of star formation, it provides a plausible pathway to explain the existence of these early quasars without violating known accretion physics. Another potential explanation involves exotic physics or mechanisms not yet fully understood. Some theorists suggest that unusual properties of the early universe, perhaps related to dark energy, dark matter interactions, or modifications to general relativity, could have accelerated the growth of black holes beyond conventional limits. For instance, dense clumps of dark matter might have created gravitational wells that funneled gas more efficiently into black holes, effectively bypassing the restrictions imposed by the Eddington limit. Alternatively, there could be unknown forms of matter or energy in the early universe that enhanced accretion rates, allowing black holes to reach extraordinary masses almost instantaneously. These ideas remain speculative, but they highlight the possibility that JWST's discoveries may point toward physics beyond what is currently described in standard cosmology. A third explanation, more controversial but no less intriguing, is the possibility that there is a fundamental flaw or limitation in the Big Bang model itself. While the Big Bang theory has been extremely successful in explaining the expansion of the universe, the cosmic microwave background, and the formation of large-scale structure, it does not fully account for the rapid emergence of supermassive black holes. If the early universe was older than current models suggest, or if the timeline of cosmic evolution differs in ways not yet understood, the formation of these massive quasars could be less paradoxical. Some researchers propose alternate cosmologies, such as models incorporating variations in the expansion rate or early periods of accelerated growth, which could allow massive structures to form sooner than predicted. While these ideas are highly speculative and would require extensive re-evaluation of observational data, the discovery of these early quasars demands that such possibilities at least be considered. Another set of explanations involves enhanced accretion scenarios, where black holes grow at rates far exceeding traditional limits. Some theoretical models suggest that early black holes could have experienced super-Eddington accretion, where matter falls onto the black hole faster than standard physics predicts, potentially due to geometric or environmental factors such as dense gas disks or anisotropic radiation. If these mechanisms were common in the early universe, they could account for the rapid mass accumulation observed by JWST. However, sustaining super-Eddington growth over hundreds of millions of years without self-limiting feedback is challenging, making this explanation plausible for some quasars, but unlikely to account for all of the observed population. The role of mergers in the early universe is also considered a potential contributor. In regions of high density, early galaxies may have collided and merged more frequently than models currently predict. Each merger would combine the masses of existing black holes and funnel gas toward their centers, accelerating growth. While mergers alone may not fully explain the extreme masses observed in less than 1 billion years. They could work in combination with direct collapse seeds or enhanced accretion rates to produce the observed early quasars. The JWST data may ultimately help distinguish which combination of processes was most important by analyzing the environments and host galaxies of these quasars. It is also worth noting that the observational data itself opens the door for new, unexpected physics. JWST's unparalleled sensitivity in the infrared allows astronomers to detect quasars that were previously invisible. This means that our understanding of the early universe may have been biased by the limitations of prior telescopes like Hubble, which could only detect the brightest and closest objects. The apparent abundance of early quasars could suggest that rapid black hole growth is not an anomaly, but a widespread phenomenon, indicating that the early universe was a far more dynamic and complex environment than previously assumed. Ultimately, the possible explanations for these early supermassive black holes fall into 3 broad categories: those consistent with extensions of known physics, like direct collapse black holes or super-Eddington accretion; those involving speculative or exotic physics, such as dark matter interactions or unknown early universe mechanisms; and those suggesting that our fundamental understanding of cosmic history and the Big Bang timeline may need revision. Each explanation carries profound implications. Confirming direct collapse black holes would reshape our understanding of early structure formation. Uncovering exotic physics could expand the laws of nature. And a fundamental flaw in the Big Bang model would rewrite the cosmic timeline itself. In essence, JWST's discovery has turned what was once a theoretical puzzle into a pressing empirical question. These quasars do not just challenge our models of black hole growth, they challenge the very framework through which we interpret the evolution of the universe. They compel scientists to explore every possible avenue, from conventional astrophysics to radical cosmological revisions, in search of an explanation that can reconcile these extraordinary observations with the known universe. The mystery of these early supermassive black holes is far from solved, and the implications will reverberate across astronomy, cosmology, and fundamental physics for decades to come. One of the leading explanations for the existence of supermassive black holes so early in the universe is the direct collapse hypothesis. This idea suggests that under the right conditions, enormous primordial gas clouds, containing tens of thousands to hundreds of thousands of solar masses, could bypass the usual stellar life cycle and collapse directly into massive black holes. Unlike the more conventional model, in which black holes form from the remnants of massive stars and then grow gradually through accretion and mergers, direct collapse allows for the creation of a massive black hole almost instantaneously relative to cosmic timescales. This mechanism provides a potential pathway for explaining how JWST has observed black holes with billions of solar masses existing less than 1 billion years after the Big Bang. The key requirement for direct collapse is the suppression of star formation within the gas cloud. Normally, as gas clouds collapse, their density increases, causing fragmentation into smaller clumps that form stars. The radiation emitted by these stars, along with subsequent supernovae, disperses gas and slows down the accumulation of mass at the center, limiting black hole growth. In a direct collapse scenario, however, specific conditions prevent the cloud from fragmenting. This could occur due to intense ultraviolet radiation from nearby galaxies, which dissociates molecular hydrogen, the primary coolant for gas clouds. Without cooling, the cloud cannot fragment into stars and remains a massive, cohesive structure capable of collapsing directly into a black hole with a mass ranging from 10^4 to 10^6 solar masses. Once a direct collapse black hole forms, it immediately has a significant advantage over stellar seed black holes. With a massive initial mass, it can grow through accretion at rates that would be impossible for smaller black holes constrained by the Eddington limit. Essentially, it starts with a head start, making it feasible to reach billions of solar masses within the first billion years of the universe. This makes the direct collapse hypothesis particularly appealing as a solution to the puzzle posed by JWST's observations, as it bridges the gap between the theoretically slow growth of black holes and the rapid emergence of early quasars. Astrophysical simulations provide support for this scenario, showing that under conditions of high gas density, minimal metallicity, and strong external radiation, massive clouds can indeed collapse without fragmenting. These simulations demonstrate that direct collapse black holes can form in halos of dark matter that provide the gravitational well necessary to accumulate large amounts of gas. The role of dark matter is crucial here. It not only shapes the potential well of the host halo, but also influences the dynamics of gas inflow, helping sustain the conditions needed for direct collapse. This interplay between baryonic matter and dark matter may explain why some regions of the early universe were conducive to rapid black hole formation, while others were not. One compelling aspect of the direct collapse hypothesis is that it naturally explains the prevalence of massive quasars observed by JWST. If the early universe contained numerous massive gas clouds in suitable environments, then the formation of multiple early supermassive black holes becomes statistically plausible. This reduces the need for extraordinary coincidences or extreme growth rates from small stellar seed black holes. Instead, it posits that the universe had the right conditions in certain regions to efficiently produce these cosmic giants, almost from the outset. However, while the direct collapse model is promising, it is not without challenges. Observational evidence for direct collapse black holes is indirect, inferred primarily from the extreme masses and luminosities of early quasars. Detecting a direct collapse black hole in the act of formation is exceedingly difficult due to the dense gas and dust surrounding it, which obscures visible light. Infrared observations, such as those enabled by JWST, are beginning to probe these early epochs, but confirming the direct collapse mechanism will require careful analysis of the host galaxy's environment, gas dynamics, and the chemical composition of the surrounding medium. Additionally, even in direct collapse scenarios, the subsequent growth of black holes to billions of solar masses requires sustained accretion over hundreds of millions of years. This means that the conditions following formation must remain conducive to rapid feeding, avoiding feedback mechanisms such as powerful quasar winds that could expel gas and slow growth. Therefore, while direct collapse provides a head start, the universe still needs to accommodate efficient mass accumulation afterward, adding a layer of complexity to the explanation. The direct collapse hypothesis also has broader implications for galaxy evolution. Black holes formed this way would already be massive enough to exert significant influence over their host galaxies, shaping star formation, gas distribution, and galactic dynamics from very early times. This early influence could explain some of the observed properties of young galaxies hosting quasars, including their surprisingly high metallicity, dense cores, and intense radiation environments. Essentially, direct collapse black holes could have acted as cosmic architects, regulating the development of their host galaxies, while also serving as luminous beacons that illuminate the early universe. The direct collapse hypothesis offers a compelling explanation for the early emergence of supermassive black holes observed by JWST. By allowing massive gas clouds to bypass star formation and collapse directly into black holes, this mechanism provides a feasible pathway for creating billion solar mass black holes in less than 1 billion years. While challenges remain, both in terms of observational confirmation and sustaining long-term growth, the hypothesis aligns closely with the properties of the early quasars now detected. It underscores the possibility that the early universe was capable of producing extreme structures through processes far more efficient and rapid than previously imagined, reshaping our understanding of cosmic evolution. Another compelling avenue of explanation for the rapid emergence of supermassive black holes in the early universe involves the enigmatic influence of dark matter. Dark matter, which makes up roughly 85% of the universe's matter content, does not interact with light and remains invisible to conventional telescopes. Yet its gravitational presence is essential in shaping cosmic structures, from galaxies to galaxy clusters. In the context of early black hole formation, some scientists propose that clumps of dark matter could have played a critical role, accelerating the growth of black holes to the astonishing sizes observed by JWST. The idea rests on the gravitational effects of dark matter halos, which act as scaffolding for the formation of galaxies and their central black holes. In the early universe, regions with higher concentrations of dark matter would have created stronger gravitational wells, drawing in surrounding gas at faster rates than regions with less dark matter. This enhanced inflow could funnel enormous amounts of baryonic matter, ordinary matter made of protons and neutrons, into the central regions of proto-galaxies, providing the raw material necessary for black holes to grow rapidly. Essentially, dark matter could act as a cosmic accelerator, concentrating gas and helping black holes accumulate mass far more quickly than they would in a uniform, low-density environment. The potential role of dark matter becomes even more intriguing when considering the distribution of early supermassive black holes. JWST has observed multiple quasars at high redshifts, suggesting that rapid black hole growth was not a rare occurrence. If these early black holes preferentially formed in regions of dense dark matter, it could explain both their existence and their clustering. Dense dark matter halos would not only provide the gravitational pull to attract gas, but also stabilize the inflow, preventing feedback processes such as quasar winds from dispersing the surrounding matter too quickly. In this way, dark matter may have created cosmic sweet spots where black holes could grow extraordinarily fast. Moreover, dark matter might influence black hole formation beyond just providing a gravitational well. Some speculative models suggest that interactions between dark matter and ordinary matter could have enhanced the cooling and collapse of gas clouds in the early universe. In standard scenarios, gas must radiate away energy to condense and form stars or black holes. Dark matter's gravitational clumping could indirectly aid this process by deepening potential wells, allowing gas to accumulate more rapidly, reach higher densities, and collapse more efficiently into black holes. While this idea remains theoretical, it highlights how dark matter could have had an active, indirect role in shaping the earliest cosmic structures. The dark matter hypothesis also interacts synergistically with the direct collapse model. In regions with dense dark matter halos, massive gas clouds might have been more likely to avoid fragmentation and undergo direct collapse into black holes. The gravitational pull of dark matter could stabilize these clouds, suppressing star formation long enough for a massive black hole to form. In this sense, dark matter may not just accelerate accretion after black hole formation, but could also facilitate the initial creation of massive black hole seeds, making it a crucial factor in explaining JWST's observations. Another intriguing consideration is the potential connection between dark matter clumping and the timing of black hole formation. If early black holes preferentially formed in regions with unusually dense dark matter, it could create a natural explanation for why we observe them so soon after the Big Bang. The early universe was not uniform. Some regions were denser, others more diffuse. Dark matter clumping could have caused these dense pockets to collapse rapidly, forming massive black holes that became luminous quasars visible to JWST. Meanwhile, less dense regions would produce fewer or smaller black holes, consistent with the uneven distribution of quasars observed. This hypothesis also has implications for the study of cosmic evolution on larger scales. Supermassive black holes influence their host galaxies through gravitational pull and energetic feedback, shaping star formation and gas dynamics. If dark matter played a key role in accelerating black hole growth, it indirectly influenced the development of galaxies themselves. Early dark matter clumps may have acted as the framework for both rapid black hole formation and the rapid assembly of the first massive galaxies, effectively orchestrating the early structure of the universe. While the dark matter explanation is compelling, it is also challenging to test directly. Dark matter does not emit or absorb light, so its distribution must be inferred from gravitational effects on visible matter. JWST's infrared observations provide indirect clues by revealing the locations and properties of early quasars and their host galaxies, but disentangling the precise influence of dark matter requires sophisticated simulations and modeling. Nevertheless, early results suggest that the densest regions in the universe, those dominated by dark matter, could indeed provide the conditions necessary for rapid black hole growth, lending credibility to this hypothesis. The dark matter role underscores the interconnectedness of cosmic evolution. Black holes, galaxies, gas clouds, and dark matter do not evolve in isolation. They interact in a complex web of gravity, radiation, and feedback. By considering how dark matter clumping could accelerate black hole formation, scientists are beginning to see a more holistic picture of the early universe, one in which unseen forces shape the growth of the most luminous and massive objects, guiding the formation of structures that define the cosmos even today. The dark matter hypothesis offers a compelling framework for understanding how supermassive black holes could form so quickly in the early universe. By concentrating gas, stabilizing massive clouds, and possibly influencing collapse dynamics, dark matter may have acted as a cosmic catalyst, enabling black holes to reach billions of solar masses in a fraction of the time conventional models predict. While further observations and simulations are needed to confirm this role, it provides a fascinating glimpse into the hidden forces that may have shaped the universe's first luminous beacons. Another possibility raised by the JWST discoveries is a far more radical one. Perhaps our understanding of cosmic time itself is incomplete. If supermassive black holes were already fully formed less than 1 billion years after the Big Bang, one potential explanation is that the universe might be older than we currently estimate. The conventional age of the universe, around 13.8 billion years, is derived from a combination of measurements, including the expansion rate of the universe, the Hubble constant, observations of the cosmic microwave background, CMB, and large-scale structure. However, discrepancies in these measurements, combined with the early appearance of quasars, suggest that our cosmic clock might be slightly off, or at least that our understanding of early cosmic epochs requires refinement. Re-evaluating the universe's age has profound implications. If the universe were older, even by a few 100 million years, it could naturally allow more time for black holes to grow to supermassive sizes without violating known physical limits, such as the Eddington accretion rate. In this scenario, what appears to us as too early might actually be consistent with a longer period of cosmic history. Essentially, the timeline inferred from redshifts and expansion models could be miscalibrated, and the early universe might have undergone processes more gradually than current models suggest. Part of this reassessment stems from ongoing debates over the Hubble constant. Measurements of the universe's expansion rate using Cepheid variable stars and supernovae yield a higher value than those derived from the cosmic microwave background. This tension, known as the Hubble tension, has persisted for years, and if resolved in favor of a slower expansion rate in the past, it would imply a slightly older universe. A universe even modestly older could help alleviate some of the paradoxes posed by JWST's observations of early quasars. If black holes had an extra 100–200 million years to accumulate mass, the challenge of forming billions of solar mass black holes in too short a period becomes less severe. Rethinking time also opens the door to more speculative but intriguing possibilities. Perhaps our understanding of time itself in the extreme conditions of the early universe requires revision. General relativity tells us that time is relative and can be influenced by gravitational fields, density, and energy distribution. In the chaotic early universe, regions of intense gravitational activity, such as those surrounding forming black holes, might experience local relativistic effects that could accelerate or skew growth in ways we do not fully understand. While this does not literally add time, it raises the possibility that our cosmic clocks calibrated for large-scale, low-gravity regions, may not perfectly represent the conditions under which the first supermassive black holes formed. Another fascinating angle is the potential for early universe dynamics to influence perceived timeframes. The standard Big Bang model assumes a relatively smooth progression from a hot, dense state to a structured cosmos, with well-defined epochs for recombination, star formation, and galaxy assembly. However, if early cosmic evolution included phases of rapid structure formation, accelerated collapse of matter, or even unknown bursts of energy, the processes that create black holes could occur on effectively compressed timescales. This would make the early universe appear to host fully formed quasars too soon relative to a uniform, slow-paced timeline, but consistent within a more dynamic cosmic evolution framework. Rethinking time also intersects with the concept of alternate cosmologies. Some theoretical models propose modifications to the Big Bang timeline, such as varying rates of cosmic expansion in the early universe, or pre-Big Bang scenarios, in which some structures already existed in proto-universe conditions. In these frameworks, the early appearance of massive black holes might not be paradoxical, but rather a natural consequence of a universe with a more complex or extended history than currently modeled. While highly speculative, these ideas reflect the depth of the challenge posed by JWST's observations. The early universe is revealing phenomena that may not neatly fit into our standard cosmological narrative. The implications of rethinking cosmic time extend beyond astrophysics to the very philosophy of how we interpret observations. It forces scientists to question the assumptions embedded in cosmological measurements. Are redshifts perfectly linear indicators of time and distance? Are our models of early galaxy and star formation sufficiently accurate to serve as a cosmic clock? Could unknown physical processes in the early universe have skewed the relationship between age and observed structure? Each of these questions underscores the complexity of the puzzle posed by early quasars. Ultimately, the idea that the universe might be older than we think is both provocative and humbling. It suggests that some of the discrepancies highlighted by JWST may not require entirely new physics, but instead a refined understanding of how time, expansion, and structure formation interconnect in the earliest epochs. By reconsidering the cosmic timeline, scientists can explore whether these supermassive black holes are truly anomalies, or whether they fit naturally into a universe whose early evolution is subtly different from our current models. In summary, rethinking time offers one of the most fundamental approaches to addressing the challenge posed by JWST's early quasars. Whether it involves recalibrating the age of the universe, accounting for relativistic effects in high-density regions, or considering more dynamic early universe processes, this perspective underscores that our understanding of cosmic chronology may not be absolute. If the universe is even slightly older than current models suggest, the rapid formation of supermassive black holes becomes more plausible, opening the door to a richer and more nuanced understanding of the cosmos's earliest moments. The unexpected appearance of supermassive black holes in the early universe has also reignited interest in alternate cosmologies, theories that question or extend the conventional Big Bang model. While the Big Bang theory has been extraordinarily successful in explaining cosmic expansion, the cosmic microwave background, and the distribution of large-scale structures, JWST's observations of early quasars suggest that it may not fully account for the formation of the universe's earliest extreme structures. Some researchers now propose that these anomalies could point toward a universe whose origins and early evolution are more complex than the standard model suggests. Alternate cosmologies encompass a wide range of theories. Some propose modifications to the Big Bang itself, such as a universe that experienced multiple phases of expansion and contraction, or one in which a pre-Big Bang epoch set the stage for rapid structure formation. In these models, the conditions for forming supermassive black holes could have existed before the conventional timeline starts, effectively giving black holes a head start. This would naturally explain how such massive objects could exist less than 1 billion years after the Big Bang. without requiring extreme violations of accretion physics or improbable growth rates. One class of alternate models is the bouncing universe scenario, in which the universe undergoes cycles of contraction and expansion rather than originating from a singular Big Bang. In such a model, some structures might survive or be influenced by previous cosmic cycles, providing a foundation for early supermassive black hole formation. While speculative, these ideas challenge the assumption that the universe's initial state was a homogeneous, featureless singularity. If matter and energy were already partially organized in some pre-Big Bang phase, the rapid emergence of quasars might not be as mysterious as it initially seems. Another intriguing set of theories involves modified inflationary models. Inflation, the exponential expansion of the universe in its earliest moments, is a cornerstone of standard cosmology, explaining the uniformity of the cosmic microwave background and the distribution of matter. However, variations on this model suggest that inflation may not have been uniform everywhere, leading to regions of higher density or more rapid structure formation. In such regions, massive black holes could have grown extraordinarily quickly, producing the early quasars JWST has now observed. These models allow for a degree of early cosmic heterogeneity that could reconcile observations with physical laws, without discarding the Big Bang entirely. Other researchers consider the possibility that the Big Bang timeline itself might need extensions or modifications. For instance, if the universe underwent phases of accelerated or delayed expansion, it could change the way we interpret high redshift observations. Redshifts are typically used as proxies for age and distance, but if the expansion history differs from the standard model, the inferred age of early structures could be off. This approach intersects with the earlier idea of rethinking cosmic time. By allowing for a more complex expansion history, the apparent too early appearance of supermassive black holes could be a natural consequence of alternate cosmic dynamics. Some alternate cosmologies even explore exotic physics beyond the standard lambda cold dark matter model. These include theories in which dark matter or dark energy behaves differently in the early universe, potentially accelerating black hole growth or altering the formation of galaxies. For example, early clumping of dark matter, unusual interactions between matter and radiation, or even the presence of previously unknown particles could provide mechanisms for rapid black hole formation. While highly speculative, these models illustrate the breadth of possibilities scientists are now considering to explain JWST's discoveries. The notion of alternate cosmologies has profound implications not only for black hole formation, but also for the broader narrative of cosmic evolution. If the standard Big Bang model is incomplete, it may mean that our understanding of everything from the first stars to the earliest galaxies requires revision. Concepts like cosmic inflation, nucleosynthesis, and the timeline of structure formation could all be affected, fundamentally changing the way we think about the universe's origin and early development. JWST's detection of early quasars is thus not just a challenge to black hole physics. It is a challenge to the foundational principles of cosmology itself. While alternate cosmologies are still highly theoretical, JWST provides an unprecedented opportunity to test them. By observing the earliest luminous objects, including quasars and the galaxies that host them, astronomers can gather empirical evidence to support or constrain these models. Each new discovery helps refine our understanding of the universe's initial conditions, the rate of cosmic expansion, and the processes that shape the formation of matter. In this way, JWST serves as a cosmic laboratory, allowing scientists to confront alternate cosmologies with real data for the first time. Ultimately, considering alternate cosmologies forces us to embrace a profound possibility that the universe's story is more complex, more dynamic, and perhaps older or differently structured than the standard Big Bang narrative suggests. The early appearance of supermassive black holes may not simply be an anomaly to patch with small adjustments. It could be a clue that the Big Bang, as currently understood, is only part of the story. Understanding these early quasars could therefore lead to a revolutionary re-evaluation of our cosmic origins, reshaping the foundation of modern astronomy and cosmology. The discovery of supermassive black holes less than 1 billion years after the Big Bang has profound consequences for astronomy as a whole, forcing scientists to revisit and reconsider long-standing assumptions about the evolution of galaxies, the formation of black holes, and the very processes that shape the cosmos. For decades, astronomers have relied on models that describe a relatively slow and orderly growth of cosmic structures. Gas clouds condense into stars, stars die and leave behind black holes, and black holes gradually grow through mergers and accretion over billions of years. JWST's observations challenge this linear narrative, revealing a universe capable of producing extreme structures in what appears to be an astonishingly short period. One immediate impact is on our understanding of galaxy formation. Previously, galaxies were thought to assemble gradually, with stars forming over hundreds of millions of years, gradually increasing mass and complexity. However, the presence of fully formed quasars implies that their host galaxies must also have grown rapidly. To host a supermassive black hole of billions of solar masses, a galaxy must provide sufficient fuel, gas and dust, for accretion and sustain a dense central environment. This suggests that some early galaxies were already massive, structured, and dynamic far earlier than theoretical models predicted. The implications are significant. JWST is showing that galaxies in the early universe may have been far more diverse and complex than previously believed. Another area affected is the study of black hole evolution. Traditionally, astronomers have modeled black holes as forming from the remnants of massive stars and growing gradually through accretion or mergers. The detection of early quasars forces a reconsideration of this paradigm, implying that black holes can reach enormous masses rapidly, possibly through mechanisms like direct collapse formation or enhanced accretion facilitated by dense gas clouds and dark matter clumping. This revelation prompts a re-evaluation of the physical limits of black hole growth and raises questions about the frequency and distribution of supermassive black holes in the early universe. Understanding these processes is essential, as black holes are not merely passive objects. They influence their surroundings, regulate star formation, and shape galactic structure through feedback processes. The JWST discoveries also reshape the timeline of cosmic evolution. By pushing back the formation of supermassive black holes and their host galaxies, astronomers now have to reconsider when the first luminous structures appeared in the universe. Epochs that were once considered too early to support such massive objects must now be viewed as periods of rapid and efficient structure formation. This has cascading effects on related fields, such as the study of ionization, the period when the first stars and galaxies ionized the surrounding neutral hydrogen. Early quasars likely contributed significantly to this process, meaning the timeline for cosmic reionization may need to be adjusted. Moreover, these discoveries have implications for observational strategies in astronomy. JWST's ability to detect high redshift quasars demonstrates the importance of infrared observations in probing the early universe. Traditional optical telescopes, like Hubble, were limited in their capacity to see through the intervening cosmic dust and the redshifted light from the first billion years. JWST's infrared sensitivity allows astronomers to directly observe early structures that were previously invisible, opening a new window into the universe's formative epochs. This capability will shape the design and objectives of future telescopes, both space-based and ground-based, as astronomers seek to map the distribution, growth, and influence of early supermassive black holes and their host galaxies. The impact extends to theoretical astronomy and cosmology. Models of galaxy and black hole formation must now incorporate mechanisms capable of producing rapid growth, such as direct collapse black holes, super-Eddington accretion, and dark matter clumping. Simulations of early universe structure formation need to be recalibrated to account for these processes, including the interactions between black holes, galaxies, and surrounding cosmic environments. The need for more accurate models will drive collaborations between computational astrophysicists, observational astronomers, and theorists, fostering a more integrative understanding of cosmic evolution. These discoveries also raise broader philosophical and methodological questions about how astronomers interpret cosmic history. Assumptions that were once considered foundational, such as the expected rate of black hole growth, the sequence of galaxy formation, and the timescale of cosmic epochs, must now be scrutinized. JWST is providing empirical evidence that the universe can produce extreme structures faster than previously thought, forcing the scientific community to balance established models against new observations and remain open to paradigm-shifting explanations. Furthermore, the early presence of supermassive black holes highlights the interconnectedness of cosmic phenomena. Black holes, galaxies, dark matter, and the intergalactic medium interact in ways that shape the evolution of the universe at all scales. Observing these processes in their infancy allows astronomers to test theories of cosmic evolution in unprecedented detail, linking the behavior of individual quasars to the broader evolution of the cosmos. The rapid emergence of these objects underscores the complexity and dynamism of the early universe, revealing that the processes shaping galaxies and black holes were far more efficient and sophisticated than classical models suggested. In practical terms, JWST's discoveries are likely to reshape research priorities for decades to come. Astronomers will focus on identifying additional early quasars, studying their host galaxies, mapping dark matter distributions, and testing the validity of competing cosmological models. Every new high redshift quasar discovered adds critical data to refine our understanding of the universe's formative epochs and the mechanisms that enabled such rapid growth. This research not only informs astrophysics, but also impacts related disciplines, including cosmology, particle physics, and the study of fundamental forces in the early universe. Ultimately, the impact of JWST's discoveries on astronomy is transformative. They challenge assumptions about the timing, mechanics, and conditions of early structure formation, forcing a re-examination of galaxy evolution, black hole growth, and cosmic history itself. They highlight the dynamic, interconnected nature of the early universe and underscore the importance of continued observation, modeling, and theoretical innovation. By revealing that the universe was capable of producing extraordinary structures almost immediately after its birth, JWST is compelling astronomers to think bigger, look deeper, and reconsider the very foundations of our understanding of the cosmos. The discovery of supermassive black holes less than 1 billion years after the Big Bang has ignited a heated scientific debate that reaches to the very foundations of cosmology. On one side are scientists who defend the Big Bang model, arguing that the observations, while surprising, can still be reconciled within the framework of known physics. On the other side are researchers who see JWST's findings as a potential sign that the standard model may be incomplete, and that a fundamental rethink of the universe's early evolution might be necessary. This debate is not only technical, but philosophical, involving questions about how we interpret data, weigh evidence, and adapt long-standing theoretical frameworks to new discoveries. Proponents of the Big Bang model emphasize the robustness of the standard cosmological framework, also known as lambda cold dark matter model, which has successfully explained a vast array of phenomena, from the cosmic microwave background to the distribution of galaxies and the observed expansion of the universe. They argue that the early appearance of quasars does not necessarily falsify the model. Instead, it may indicate that certain processes, such as black hole accretion or direct collapse formation, are more efficient in the early universe than previously modeled. According to this perspective, JWST's discoveries are an opportunity to refine existing theories rather than abandon them. For example, defenders of the standard model point to super-Eddington accretion as a potential explanation. In this scenario, black holes can grow faster than previously assumed by accreting matter at rates above the classical Eddington limit, especially under the dense conditions of the early universe. They also suggest that interactions with dense gas clouds, mergers between smaller black holes, and the influence of dark matter could combine to accelerate growth without requiring modifications to the Big Bang timeline. In other words, the universe might be fully consistent with the standard model if these extreme but physically plausible mechanisms are accounted for. On the other side of the debate are scientists who see JWST's discoveries as evidence that something more profound may be at play. They argue that the sheer mass and brightness of these early quasars, appearing so soon after the Big Bang, strain even the most optimistic growth models. If black holes formed from stellar remnants, reaching billions of solar masses in under 1 billion years is extremely difficult, even under super Eddington accretion or direct collapse scenarios. To these researchers, the observations suggest that the standard cosmological timeline may be incomplete, or that unknown physics could be influencing early black hole formation. Some advocates for a rethink point to alternate cosmologies as a potential solution. They propose that our understanding of the Big Bang may need to be extended or revised, incorporating scenarios such as a universe older than currently estimated, non-standard expansion histories, or pre-Big Bang phases that allowed massive structures to form earlier than expected. In these models, the early emergence of supermassive black holes is not an anomaly, but a natural consequence of a more complex cosmic history. While speculative, these proposals underscore the willingness of the scientific community to entertain bold ideas in light of JWST's unprecedented observations. The debate also highlights the role of observational evidence in shaping theory. JWST's ability to detect early quasars provides direct empirical data that must be reconciled with theoretical models. The discussion is no longer purely speculative. Astronomers now have concrete examples of extreme early structures. Each new high redshift quasar challenges theorists to explain how such objects could exist, driving a productive tension between observation and theory that is fundamental to scientific progress. In addition to technical disagreements, the debate carries a philosophical dimension. Some researchers caution against over-interpreting the data, noting that our understanding of the early universe is still limited and that anomalies often resolve as more information becomes available. Others argue that these discoveries are precisely the kind of data that should prompt a re-evaluation of foundational assumptions, reminding the scientific community that models, no matter how elegant, must ultimately accommodate reality. This debate is also influencing the direction of future research. Teams around the world are now prioritizing the identification of additional early quasars, precise measurements of their masses and host galaxies, and detailed studies of their environments. The goal is to gather enough evidence to determine whether JWST's discoveries represent rare exceptions, extreme but plausible cases, or signs of a deeper gap in our understanding of cosmic origins. Conferences, workshops, and collaborations are increasingly focused on this tension between defending the Big Bang framework and exploring new theoretical possibilities, highlighting the vibrancy and dynamism of modern cosmology. The scientific debate illustrates a core principle of science itself. Theories are only as strong as their ability to explain observations. JWST has provided a profound challenge, forcing astronomers to examine every assumption about early structure formation, black hole growth, and the evolution of the universe. Whether the resolution lies within the standard model, requires minor adjustments, or demands revolutionary new thinking, the debate underscores the vitality of astronomy as a field that thrives on questioning, testing, and revising our understanding of the cosmos in response to new evidence. In summary, the scientific debate over JWST's early quasars reflects a clash between tradition and innovation, between defending well-established models and exploring radical alternatives. It is a dynamic, high-stakes conversation that has implications for our understanding of black holes, galaxies, and the universe itself. By confronting these extreme observations, astronomers are not only testing the limits of current theory, but also laying the groundwork for potentially transformative insights into the nature and origins of the cosmos. The James Webb Space Telescope, with its unparalleled sensitivity and infrared capabilities, is poised to continue revolutionizing our understanding of the early universe through the search for even earlier quasars. Its current discoveries are only the beginning. Astronomers anticipate that JWST will identify a growing population of high redshift quasars, some potentially forming mere hundreds of millions of years after the Big Bang. Each additional detection will provide crucial data to test theories of black hole formation, galaxy evolution, and the broader timeline of cosmic history. JWST's advanced instruments, such as the Near-Infrared Camera, NIR-CAM, and the Near-Infrared Spectrograph, NIR-SPEC, allow it to peer deeper into the universe than ever before. By capturing light that has been redshifted into the infrared due to the expansion of the universe, JWST can observe objects that existed at epochs previously inaccessible to astronomers. This capability enables the study of the earliest quasars not just as isolated phenomena, but as part of the larger context of galaxy formation, star formation, and cosmic ionization. Future JWST missions are likely to focus on systematic surveys of the high redshift universe, mapping regions of space that may harbor nascent quasars. These surveys aim to determine how common these supermassive black holes were in the early universe, whether their formation was a rare anomaly or a widespread process, and how their growth influenced the development of surrounding galaxies. Observing the environments of these quasars, such as gas density, dark matter distribution, and the presence of companion galaxies, will provide vital clues about the mechanisms driving rapid black hole formation. Moreover, JWST will help refine measurements of quasar masses, luminosities, and accretion rates, providing direct observational evidence to test competing theories. Are these black holes growing primarily through direct collapse, rapid accretion, or mergers with other black holes? Are there environmental factors that consistently accelerate their growth? Each new dataset will either support current models or reveal inconsistencies that challenge our understanding of the early universe. These future missions also have the potential to deepen the mystery. Should JWST detect quasars even earlier than current predictions allow, existing theories, including direct collapse scenarios and dark matter-assisted growth, may struggle to provide explanations. This would suggest that the early universe was even more dynamic, complex, and extreme than imagined, possibly pointing toward new physics or necessitating revisions to the timeline established by the Big Bang model. Every quasar observed at these extreme distances serves as both a window into the past and a test of our most fundamental cosmological assumptions. In addition to quasars, JWST's future observations will shed light on the galaxies hosting them, revealing the interplay between black holes and star formation in the universe's infancy. This holistic view is essential as black holes and their host galaxies evolve together, influencing each other through feedback processes. Understanding this relationship in the earliest epochs will provide context for the rapid emergence of supermassive black holes and illuminate the conditions that shaped the universe as we observe it today. Ultimately, JWST's ongoing missions promise to expand the frontier of knowledge in ways previously unimaginable. By searching for even earlier quasars, the telescope will either confirm the emerging patterns we see or push the boundaries of mystery further, challenging astronomers to rethink the origins, evolution, and fundamental nature of the cosmos. Each discovery brings us closer to understanding how the universe evolved from a near-uniform primordial state to the richly structured, luminous cosmos we inhabit today. As JWST continues to peer deeper into the cosmos, its discoveries raise a profound and unsettling question. Did we just uncover cracks in the Big Bang theory, or are we witnessing the dawn of a new cosmic revolution? The detection of supermassive black holes less than 1 billion years after the universe's birth challenges one of the most established pillars of modern cosmology. For decades, the Big Bang model has provided a coherent framework for understanding the expansion of the universe, the formation of galaxies, and the evolution of cosmic structures. Yet, these early quasars seem to defy expectations, existing at a time when the universe was thought to be too young to produce such extreme objects. If these observations are confirmed as representative rather than anomalous, they could indicate that the standard cosmological timeline is incomplete. Perhaps the universe is older than we thought, allowing black holes more time to grow. Perhaps unseen processes like direct collapse black holes or dark matter-assisted accretion dominate early cosmic evolution. Or perhaps the universe's early expansion and structure formation are governed by physics that we have yet to discover. Each possibility forces us to reconsider the very mechanisms by which matter, energy, and gravity interact to shape the cosmos. The implications go beyond black holes. Quasars are cosmic lighthouses, illuminating the intergalactic medium and influencing the formation of surrounding galaxies. Their early existence implies that the processes governing galaxy formation, star formation, and cosmic reionization occurred much faster and more efficiently than previously believed. This challenges not only the timeline of the universe, but also our understanding of the conditions that allowed life-bearing galaxies to emerge billions of years later. In essence, these discoveries touch the foundations of cosmology, astrophysics, and our broader conception of cosmic history. The scientific community is now at a crossroads. On one hand, defenders of the Big Bang argue that current theories can accommodate these findings with refinements, pointing to mechanisms like super-Eddington accretion, dark matter clumping, or direct collapse scenarios. On the other hand, some researchers suggest that we may need a more radical rethink, exploring alternate cosmologies, modified expansion histories, or new physics that could explain the rapid appearance of massive quasars. This debate embodies the dynamic nature of science. Theories must bend or break in the face of compelling evidence, and no model, however established, is immune from revision. JWST's discoveries invite a humbling reflection on our place in the universe. The cosmos is not a static, predictable system, but a vast, evolving arena where extremes are not only possible, but perhaps commonplace. Supermassive black holes forming in what we once considered the universe's infancy remind us that our knowledge is provisional and that each new observation can radically reshape our understanding. The telescope is not just observing distant objects, it is probing the limits of human comprehension and challenging assumptions we once took for granted. The closing mystery, then, is profound and open-ended. Are these early quasars anomalies to be explained within the Big Bang framework, or are they signposts pointing toward a deeper, more complex understanding of the cosmos? Will the coming decades of JWST observations reveal a universe that fits neatly into existing theory, or will they force a revolutionary shift in cosmology, reshaping our understanding of time, matter, and the origins of everything? Every new quasar discovered at extreme distances is a question mark written across the sky, asking us to reconsider what we know and what we have yet to learn. In the end, the answer is not yet known, but the journey itself is transformative. JWST has opened a window into a universe far stranger, more dynamic, and more mysterious than we imagined. Whether these discoveries mark the first cracks in the Big Bang theory or the threshold of a new cosmic revolution, one thing is certain: our understanding of the universe will never be the same. The early quasars beckon us forward, challenging us to explore, question, and expand the frontiers of human knowledge, and reminding us that the cosmos still holds secrets far beyond our current grasp. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.